give us your microphone.
Oh, sorry.
Okay. Shit. Okay, I'm going to stop sharing for a second. Do you mind just kind of share screen? Yes, it's okay, well, we set this up. I'm going to just introduce our last speaker of this morning session. We have Yousef Alnaser.
Yeah.
Yes, great.
Awesome.
Yeah, Yousef Alnaser works at Fraunhofer ENAS, located at Chemnitz, Germany. He's also affiliated with Technical University of Chemnitz. His main work involves around accelerating computer-intensive algorithms such as image processing, medical simulation, and also machine learning algorithms. And he mainly uses FPGA as the acceleration platform, either on edge or high-end accelerator cards. And he's going to give us today a talk regarding a reconfigurable FPGA-based machine learning library for kernel methods. Welcome, Yousef. Please go ahead.
Thank you very much for the introduction. I hope you can hear me well.
Yes.
So I'm really excited to be here, not just because I love FPGAs, I think everybody does, but also just to talk about or bringing together 3 different subjects, mainly reconfigurable computing or reconfigurable FPGA-based computing, along with machine learning. These 2 are rarely together nowadays, but I hope we can bring them together. And so I think let's dive in. This is a machine learning algorithm library designed specifically for kernel methods for big data in general. And there's also, on top of that, like a Python interface to it, so we don't scare away software folks, because they really get scared away really easily by FPGAs. And I thought maybe we can begin by a little bit of intuition. What is kernel methods, or what are kernel methods? And here, for example, I will show only this is really slow, the kernel ridge regression algorithm. And the intuition behind it is, first of all, we introduced linear regression. I think everybody knows this already. Tries to estimate the data. This is a sine wave, and it tries to predict it, but it's poorly predictable because the data is nonlinear. But then if you add ridge regression, then you can, if you have cases of overfit, ridge regression can help you with that, just like steering away from overfitting. But then kernels come into place, and kernels tend to overfit because they want to take into consideration all data in mind. And when you put all of this together, kernel ridge regression, then you will get really nice estimators that correctly estimates more or less the sine wave. So the key takeaway from here is that kernel ridge regression, or kernels in general, or kernel methods, are very useful for nonlinear and complex data. And this is why we want to target them, because they're useful generally in the industry. And of course, kernel methods requires kernels, and kernels are a bit hard to deal with. And to show you this, for example, this is some kernel called radius basis kernel, the RPF kernel for short, and it requires computing and storing an n by n matrix. And if you think of that in floating point, this is really big. So it has an n squared d compute complexity and n squared storage complexity. And to even convince you more of that, we went to the UCI data set and just pulled all of the regression data sets in there. And we drew them in this diagram where I show you here. It's color-coded for the flops you need to construct the kernel matrix. And I think, yeah, the lines appear there. And then we have this line here that that tells you how much RAM you need, or storage in general you need. And this is the 1 terabyte RAM you need just to compute to store the kernel matrix. And the curved line here is the 1 teraflop you need to compute the kernel matrix. So in short, kernel matrices are really hard to deal with, just like Verilog, I think. But then our idea is just to have an FPGA library that contains some of the most famous kernel methods. For example, kernel edge regression, support vector machines, Gaussian processes, and principal component analysis. And then sets a machine learning scientist where he just can import these libraries or one of the libraries he wants and run them as he would in any computer, in any Python IDE, for example, in Jupyter Notebook. So that way he will be comfortable with dealing with that. But internally, it will be mapped to different FPGAs or whatever the FPGAs you have. So think of it as a plug and play. You just plug in your FPGA or connect to it if it's in a data center. And then this, what we are trying to build is it will map there accordingly. So maybe it's an edge device or maybe high-end accelerator devices. It should work with most. So why are we building this library, or what's the useful of this? Is that as of now, we get approximately 30 times runtime improvement over Python CPU libraries, for example, scikit-learn or SciPy. We use partial reconfiguration to support different kernels because I showed the RBF kernels, but there are a lot of different other kernels there, and we want to support all of them easily, and hence we use the partial reconfiguration to do specific kernel operations, and also the library size because of, if you want to, maybe we'll come to that later, but with partial reconfiguration we will get a reduced library size. And also, since it's modular, it would be easier to extend, add more kernels, add more solvers, and it works with big data out of the box. No FPGA wizardry is required from a software point of view or a programmer point of view. So let's dig deep. And the first, we want to see the kernel ridge regression part. I don't want to get into so many equations, to be honest. Just we'll keep it high level. But the essence of it is that we have the matrix A here that has a size of n squared. And this is where our problem is. And we want to find x that best describe the data output, which is y. And to do that, we use the CG method. So the CG method is a well-known conjugate gradient method, is a well-known method used in machine learning. It looks like this, a bit scary, I know, but I want to give or direct your attention to just the few operations that we have here, only those that are marked. Here we see some kernel calculations with a K here. So this is where we construct the kernel matrix. So we have to build it first, and then we have to save it into memory, and this is where the A is, and then reuse it again one time here, followed by a vector multiplication. So we multiply the matrix with a vector, and another time inside the loop here. So we have to do this iteratively in order to solve this system of linear equations. And those operations that I showed you have quadratic complexity, and that's what's important. The others are already fast, so why accelerate stuff that are already fast? We only concentrate on the crucial parts here. And this would be run on an FPGA that we use it as an accelerator. So this is really a different domain of what FPGAs can do. So this is not, the FPGA is not a helper here, it's the main compute platform. And the remaining stuff will go into software, for example, the ARM cores that already are included in most FPGA standalone boards. And then the algorithm changes a little bit, where we just have, where we calculate the kernel matrix and the multiplication afterwards. But the problem is we still have the storage issue. So we don't want to store the kernel matrix because you don't have enough RAMs. If you're dealing with 4 or 5 or maybe 10 terabytes of RAM, not giga, this is tera, then it's really hard to accomplish that in general. So what we want to do is calculate it on the fly whenever we need it without explicitly saving it. And this is the main idea here, but that will introduce two problems. First, the algorithm would be slower, hence why FPGAs are there to accelerate it. Second, the bandwidth memory. Since we're not saving it and we're recalculating it every time, and to calculate it, you need to input some data from memory, then you have a high bandwidth memory. And to solve that, this is the Same old matrix tiling or partitioning just to promote data reuse, and then you don't have any bandwidth issues anymore. And if you choose the tile size carefully, then you would basically reduce all bandwidth requirements. As an the accelerator overview looks kind of like this. Basically, 3 parts, or main 3 parts. The first part is the KM, which is kernel matrix construction, where we calculate it. We calculate it partially. This is why we have the prime here. And then we have a dynamic region where we just put different kernels inside. Or maybe more precisely, kernel-specific operations. And then we follow it by matrix vector multiplication. We embed the DMs, as you can see here, inside the modules itself, for example, KM and MV, and we will come to why we do that later. So, as I said, and this is all done in HLS. Yeah, I know real hardware developers still use HLS. Maybe it's hard to believe, but it's still there. It's really powerful, and we will showcase why it is powerful in our case. This is approximately 300 lines of code, so easy to manage, to build, to test even, and to change if you want to do amendments to your design. This is all compile time configurable and runtime compatible with any arbitrary data size. So this is targeted for big data that don't typically run on your machine learning or will run slower on your machine learning workstations. This is a list of the supported kernels that we can currently do. Of course, we don't care about the math very much, but what I want to bring your attention to is these operations. So the RPFs have, the kernels are well established in this community, but we want to look at it from a computational point of view. You can notice that there's 2 main operations in the supported kernels at the moment, the norm of the difference and a dot product, and that's it. And because our target is dynamic regions or partial reconfigurations, we want to reduce the dynamic region size as much as possible. So we want to put everything as much as we can in the static regions. And for that, we had this typical adder or dot product adder tree, so a parallel multiplication followed by an adder tree, and then we have a little bit of logic behind just to change between if we want to do, for example, in this case, the norm of the difference. This emanation is slow. But then again, if you want to do the dot product, then it takes a different path just to do the same. And in that way, we can combine both operations in just one design in the static region. Followed by that, then we can do the reconfigurable models for different kernels. And this is where we put only kernel-specific operations. That way, the dynamic region would be as small as possible. As for the kernel matrix partitioning, yeah, we use, this is a typical partitioning algorithm that I think it's really famous, where we just have the kernel matrix shown here as an A, and it's styled by T by T, size is T by T, and T should fit ideally into, or will fit into memory. So whatever local memory you have inside your FPGA, VRAM, I mean, is T will fit there, and then you can compute only the upper triangle of this matrix, reducing the runtime by 2, because it's a triangular matrix, so we only do that. So we only calculate that. And then we followed a multiplication with the vector P, for example, to get a vector Q. So it's a matrix construction plus matrix vector multiplication. Everything here, for example, T and F, and is compile time configurable if you want to change the tile size or how many parallel features you want to do in, you want to process in parallel. D and N are the dataset specific terms, and this is compatible basically with any arbitrary dataset. Of course, we don't do this naively. Even inside the tile, we do extra partitioning called microtiles. Microtiles sounds fancy, but it's just a term we make for parallelism. So we don't compute one element at a time from the matrix from the matrix A. We calculate multiple elements in parallel, fully Another case for kernel methods, Gaussian processes, and this is pretty much used also in the industry. It follows the same logic, so it's a new algorithm, but it's the same thing all over again. We have 3 kernel matrices that we have to compute, K, K star, and K double star with different sizes, and we follow the same thing. We construct the kernel matrices in the hardware, and then we give it to the software to continue on with the linear complexity stuff that are easy to calculate. And this is where the reuse of the same IP that we made still works there. Speed, favorite topic. And this is like a diagram. I mean, first of all, we wanted to compare, of course, our results with other existing simulators. And we kind of didn't find any that follows the same thing that we do, which is matrix computations in tiled fashion for this specific instances. But we saw what's out there. So there's the scikit-learn. They use the Cholesky method. This has cubic complexity, and we're dealing here with the quadratic complexity. So this is completely out of the question. And they don't do this on-the-fly calculation of the kernel matrix. They have to calculate it, save it into memory, and if you have big data sets, then it won't be saved. Other implementations like CG, for example, here, it's a combination of scikit-learn and SciPy, where it calculates like our algorithm with the CG method. And this is where you see the blue line at first, and the orange line is our accelerator running on the FPGA. By the way, this is run on one small Kria board, and this is where the results are from. But in principle, we could use more Kria boards or even more bigger accelerator cards. And at first, you can see here the Python implementation is a little bit faster for up to approximately 18,000 data points in your data set. This is expected because they calculate the kernel matrix and save it into memory. They don't recalculate it on the fly as we do. And once the data set size increases, then you can see that the memory latencies come into play, and then it's slower up until a point where you just cannot continue further because we're out of RAM. But our accelerator just keeps going. And this approximately achieves 30 times faster at the best case. And the orange and the green line is the same implementation, but with Python, like the same our implementation, but with Python. This is where the important part is. This is, whenever I see this slide, I think of stock markets because it's a lot of percentages, but I just want to give you a look about the sizes for example, if you do an all static implementation, then you get an 8 megabytes for each implementation. If you do it with PR, then you get only 8 bytes, and then with different kernels, only approximately 3 megabytes per kernel implementation. This gives approximately 40% reduction in the size of the library that we want. This has a trade-off, of course, because we use more resources that way because of the next slide that I'm going to show, which is the challenges we faced. And I think this is the most important part that we want to share here, is that because of the PR logic, you have to allocate the region that accommodate the largest kernel. And then the smaller kernels will have wasted resources or underutilization. This is something that we have to live with if we want just to reduce the library size. And we will use Vivado for the BR region. So this is all Xilinx products. So we did the floor planning by ourselves. And I mean, it's really hard to draw a line where you just say, okay, I want these DSPs and not those. This is really hard to do. We wish there would be more automatic way to do this goodly. I mean, there is some ways, but it didn't work for us. And as you know, in Vivado, in the PR story in Vivado is not well documented, and we had to do a lot of trial and error. Also, this is called HLS, but it's not actually HLS. It's more a general topic, the single cycle accumulation, because all of our computations are single precision floating point. And it's really hard to do it in some of the UltraScale Plus devices, for example, the Kria, because it uses the SP48. And the single cycle accumulation we needed for acceleration, we did it anyways, but we had to do a lot of math and a lot of tricks in order to do that of course, HLS still, the HLS compiler still predicts incorrect dependencies, and you have to outsmart the tool chain in order just to tell it, to convince it that I don't have any dependencies in my loops. And for data movements, yeah, we used manual data handling. Of course, this is we need, but for the DMA logic core from Xilinx, we did not use that because even in the basic mode, it requires a lot of CPU power. Then we don't have any accelerations. But in the scatter-gather mode, it requires a huge number of descriptors because our matrices are really big. We're dealing with a million number of instances and small tiles. Then we have to generate a lot of buffer descriptors. So last slide, in summary, then we have our library that contains 3 implementations, one for kernel construction with multiplication afterwards, one with kernel constructions only, but only the upper triangle, and one with the full matrix. And with HLS, you can do this in a day. Maybe 4 hours, you will just do the changes that you want and verify it. But in VHDL or Verilog, it was really hard to do because you have to change a lot of files. This is thousands and thousands of lines of code. For the algorithms, we have KRR and GP, and then we can use our implementation, whatever implementation we want, to target our machine learning algorithm. We hope next we will do the support vector machines and the principal component analysis to add it to our support of ML algorithms, and we will also do the AI engines, and as always, more kernels. The more kernels we have, the better for the software guys to actually be convinced that to use this machine learning library. And that's it. Thank you for your attention. Maybe one more point that if you want to use that, because it's still not open source, it is open source but not well documented to be released to the public if you want to use it or work together on it, or even if you just want to complain about Vivado, there's my email. You can just contact me anytime you want.
Thanks, Yousef. That's actually going to be my question on how we want to use it.
Yeah, sure.
Questions for Yousef? I guess I have no. OK, Chan, go ahead.
Nice work, but I'm wondering what if you just compile the kernel method in C++ and run it on CPU?
Can you repeat that? Sorry.
How would the performance be if you just compile the algorithm and run it on CPU? Because if you run it in scikit-learn, it's known to be not very optimized.
I mean, this is what I showed one of the slides. If you just compile it, compile the algorithm, there's a lot of animations here. Maybe I can do that.
Yeah.
If you compile the algorithm, it's this slide. If you compile the algorithm on a CPU, then you will get 80 times less compute time, or sorry, 80 times worse compute time. So, and this is what we tried.
In which?
This is the green line, as you can see.
But that's native Python.
Yeah.
And I mean, if you compile it in C++ or other language instead of a scripting language,
it would still be in the same category. So we tried also C++. We get slightly better results. So instead of 80 times worse, it was maybe in the range of 75 times worse. So it didn't help that much in.
You are saying it is slower than native Python.
Excuse me? You
are saying that it is slower than native Python.
No, it is as same as native Python. Approximately the same. In C++, we didn't have any much compute difference. What made the difference basically is how big your tile is in order to fit it into your cache. So the CPU, the cache of the CPU is actually what played a crucial role there.
OK, thank you.
Go ahead.
So yeah, I wanted to ask about the same slide, basically, because you're comparing hardware with programming language. So I guess it's always the underlying CPU that does the computation. Mm-hmm. And it will be very, very interesting to see also how, if you benchmark against a GPU, right? And see a dedicated distributive unit, how well it does. Because you're using the FPGA as an accelerator, basically. And it'll be very, very interesting to see how much you outperform the GPU.
Yeah, that's coming hopefully in the few coming months, to do the same implementation on GPUs. We opt for FPGAs because for me it's easier. It's there, we have it. GPUs, we also have GPUs, and we have some implementations on GPUs, but we're not quite there to just say this is better than this.
The Kira board you mentioned, it has no PCI or so, if I remember right. How did you interface with the FPGA, and what part of the time do you need just to send down the data and get it back? Okay,
so basically because the Kria SOM has already a CPU, ARM cores with RAM installed there, so you can interface that with Xilinx products in PYNQ. In the PYNQ interface, this opens like a Python-based interface that you can just talk to. And from a user's perspective, and this is where the target goal of that library is for software people to use it, it would be much easier for them if they just see a Python or a Jupyter notebook and they work with that instead of going deeply on what we deal with generally in our everyday life, not theirs. So that's that. And for the other cases where we have a PCI Express, so the host CPU would actually talk to the FPGA and sends all the data. The data that we need is the time to send the data is quite minimal because we only need to send the first tile, and this is where the latency comes from. But then the other tiles will be sent while we are computing the tile that we have currently now. This is like ping-pong buffering, really straightforward that hides all latencies.
Because I actually have another question regarding what you said is currently partially configurable in the sense that you had to manually do floor planning.
Yep.
I was wondering how this is going to work if you want to, if you want someone else to use it. I suppose is it going to come with recommended floor planning for the
No. So yeah,
chip?
that's the thing. If we want to do it, of course. If you want to duplicate the work, then you would have to do the full planning, and I hope you do better job than we do it. But from a user's perspective, this is all hidden. I mean, the library is already compiled. We already have the bit streams, and the user just, as I showed, they will just import the library that they want, and they would be mapped accordingly. So it will be a pre-compiled library. But if you want to duplicate the work, yeah.
Okay, I see. So so it comes with like I guess some FPGAs.
Yes.
Right.
Yeah.
Like the ones you show, like
yep.
Zinc and stuff. Okay, cool. Any other questions for Yousef?
Super, then we're early.
All right.
Nice.
Let's thank Yousef again for the very nice talk. And, good. All right.